Hi everyone, thank you for joining me as we talk about connecting students with 3D science as we talk about virtual phenomena. Now when we talk about 3D science and a phenomenon, it's useful to check out this graphic. When we think about students in the three-dimensional science classroom, their role is kind of elevated, where they're synthesizing, investigating, and communicating information. So we have a phenomenon or a problem or a scenario that students figure out as they are using the science and engineering practices and the cross-cutting concepts. And the final piece for them is they are constructing explanations or possibly arguments and communicating that to the teacher as we facilitate their science learning. So one really important piece about three-dimensional science is the importance of a phenomenon. Now, an effective phenomenon requires the core idea to explain or figure out. In other words, it's something that students, as they try to figure out what's going on with this problem or phenomenon, they're learning about the core idea or the content. An effective phenomenon is observable, so maybe it's something students can have their hands on or maybe possibly see outside, or even through media like video or audio possibly. And a phenomenon engages students in sense making. And also, an effective phenomenon does not have to be phenomenal. In other words, it doesn't have to be over the top or require crazy materials. These are things we just want students to be observing. Now, an excellent resource for you to view is the Georgia Science Teachers Association Phenomenon Bank. It is a free resource on their website, and you can search by grade or course, by standard, and see phenomena that are submitted by science teachers here in Georgia. When we talk about doing this virtually, we have some options. First, we could show students a video, maybe one that is teacher created or one that is already available online, to kind of pose a question or a challenge at the start of a unit or lesson. But some things to keep in mind when using video. First, just like when we're meeting face-to-face, the video should create a drive for the students to figure out that phenomenon. In other words, that video, teacher created or online, should engage students in trying to ask questions and then work towards explaining what's going on in the phenomenon, but at the same time not give away too many of the key ideas that students are going to develop as they go through this sequence. But they don't have to be technology based. There are ways we could introduce phenomenon without having to show a video too. Also, get the family involved. If students are at home, they could be designing investigations, working on models, and things like that with their siblings or with other people in the house. The important thing to consider is we're creating valuable learning experiences. So it's really important that students have time to think, predict, and explain as they go through this sequence virtually. Check out this example. So in this example, we have two 8th grade science standards. And I want you to notice in these standards the color coding. Each standard starts with the science practice of obtain, evaluate, and communicate information. But in addition, notice how that color coding corresponds to the individual standards. So with this phenomenon, we're going to have students to develop and use models to describe the movement of particles as we remove or add thermal energy. We're also going to have students plan and carry out investigations on the effects of heat transfer on molecular motion. So with these science practices here, students need to be communicating with their models. The models aren't just for them. They need to communicate what they've learned with that core idea. And with the second standard, students are obtaining information as they plan and carrying out an investigation. Let's take a little further look into the phenomenon task and what students will be doing. So first, students are going to start with an investigation. So we introduce this phenomenon and they start with an investigation. This lab isn't something that they do at the end of the learning structure. They're actually getting information initially with this. And after that, they start to develop questions to help them get more information about how that matter changes when we add energy. Now in this slide, we have color coding here again. In the blue, we have the science and engineering practice. In the green, we have the cross-cutting concepts. So in everything that we have the students doing, we have them involved with the science practice and involved with the cross-cutting concept at the same time. And eventually, students work through developing a model and finalizing their model And we'll bring the whole group back together with a discussion. And you can see here how we go through the obtain, evaluate, and communicate sequence. It's not just about students memorizing the information, how they're going to process it, how they're going to evaluate it, and how they're going to communicate it out. So, check out this video introduction for this phenomenon.
Hey everybody. Alright, so I have two surfaces here, and I want to see if ice is going to be melting differently on these two surfaces. Now, I want you to think about this and make a prediction. Now, maybe you don't have these two surfaces at your house, but that's okay. Just any two different surfaces work. So, we're going to put ice cubes on these and see what happens. Now, in your prediction, I want you to include a diagram. What would the ice look like at a really small scale between these two surfaces? So, think about that. In your prediction, include that diagram, and check back for the result in the next video.
Okay, so that video was just the first part to this phenomenon sequence. It's so important that however we structure this, with or without technology, we allow some room and time for wonder. Students need that wait time so they're able to develop some initial ideas or initial models and explanations towards that phenomenon. So we can then respond to those initial ideas with or without technology as students are developing those core idea understandings. We can provide some suggested readings to help them as maybe they design their own investigation or start working towards some models. Now there are so many ways we can respond with technology, so we can really use what our systems already have and what students are already comfortable with. But we should consider establishing some norms. Students may not be comfortable responding with some of the technology tools, or maybe putting some of their thinking out there for the whole class to see. So we really should consider that when designing a phenomenon sequence like this. And also, we need to be flexible. Even more important that we chunk what we're giving students so they have the time and the space to develop those core ideas and explain that phenomenon. And finally, equity considerations are also important. In addition to access to technology and resources, when we have students designing investigations and developing models, it's really important we consider what they may or may not have access to around their own house. So after allowing students time to develop initial models and explanations, or respond to their initial models, we could then have a follow-up, bring the whole group back together possibly, and discuss the phenomenon or some of the core ideas that were presented. So check out part 2 of this video.
Alright, so here's the result. Is that what you predicted? The metal piece melted the ice a whole lot faster than the tile did. The tile one's barely melting. Now, why does this happen? Did you do surfaces like this or different surfaces? Did your prediction match what the result was? Or why does this happen? Let's dig deeper into this.
Okay, so here are the results from my own daughter. And you can see with this phenomenon, there's a prediction before the actual investigation. We have an initial model here too that was produced, and we have the initial result. Now, what's great about this is we can have students share their predictions or share their initial models at the forefront of this phenomenon task. And there are so many options we can use in the virtual space to do this. And if students aren't comfortable with maybe recording a video of them talking, they can still have maybe pictures of diagrams like this or other things that you and your students have access to. Students should be hearing other people's models or suggestions or predictions and even some of the initial explanations too. Now, the lesson doesn't stop here. After this next video and this next piece, students may have some suggested readings, maybe some articles that they can read about the molecular motion or some of the heat transfer that they were involved with. Maybe students could be testing other surfaces, whatever they have around the house. The important thing is, though, students have time to refine and correct any initial predictions and initial models. This is just the first piece. We could bring the students together for a group discussion with whatever technology students and you have access to. But what's really important is, throughout this task, we're taking students through the obtain, evaluate, and communicate sequence. And that's what we're aiming for, meaningful learning experiences. So, just because we have to do this virtually doesn't mean we have to cut those parts out. So as you move forward designing lessons in the virtual space, think about how we can still have that phenomenon driving what students do in creating meaningful learning experiences. Thank you for joining me today. My email's here on the slide. Please reach out with any questions about this or other things, and consider following us on Twitter at GaDOE Science. Thank you so much for your time.